So here we will see a sample problem. Okay, so it says the figure A shows a circuit that contains 3 identical resistors. This one, with resistance R equals 9 ohm. 2 identical inductors with inductance L, 2 millihenry, and an ideal battery. This is ideal battery with EMF E equals 18 volt. So what is the current I through the battery? This is I. So we would like to find this I just after the switch is closed. So actually, yeah, what we need to remember, in fact, we need to remember is that, so we have a VL, actually not directly related to this problem, but maybe I just add a page here. So what we need to remember is that VL equals L di dt, and also C IC equals V dV dt, C dV dt, like this. So which means that the current of inductor is continuous, and here the voltage of capacitance is continuous. So for the voltage of the is not necessarily CESS necessarily continuous. So as the I of C is not necessarily continuous. Okay, so in this case, we will use the fact here that the current of L is continuous. So before the switch is closed, of course there is no current. There is no current going through the inductor, which means that just after the switch is closed, then IL 0 minus equals 0, and as it is continuous, which means that IL 0 plus is also 0, which means that there is no current going through this path just for T equals T plus, and there is no current going through this path. So only current going through here, which means the current I here should be E over a single R, because this path is open, this path is open. So it is actually 18 over 9 ohm, which is 2A. So I think most of you in circuit analysis, you know how to calculate this one. And what is the current I through the battery long after? The keyword here is long after the switch, which means T tends to infinity. And T tends to infinity. And suppose we know the response will be something like that. And if T tends to infinity, this whole term will shrink to 0. So, which is like the inductor doesn't really exist. Since it is similar to that case, which means for T tends to infinity, you can just ignore this one. You can just regard it as a wire. So which is like 3 resistance in parallel. So R equivalent is nothing but R parallel with R, which is R over 3. Okay, so in this case, the current going through the battery I is E over R equivalent, which is 18 over 9 over 3. Now the 3 is 3, so this is 6A. Okay. So this is easy, I think. Okay, so next, we have another sample problem. So it says a solenoid has an inductance 53 millihenry and a resistance of 0.37 ohm. If the solenoid is connected to a battery, how long will the current take to reach its half of its final equilibrium value? So it should be like something like this. So there will be an equilibrium because which is like it is like something like I equals E over R 1 minus exponential to minus let's say RT over L. Yeah, something like that. So when T just now I just mentioned that when T tends to infinity, this term will be 0. So I maybe I call it final will be nothing but E over R because this term is 0. So which means this whole term is 1 minus 0. So this is 1 times this one is actually this one. Okay, so this is called the equilibrium equilibrium value here. And if it asks the current take to reach half is equilibrium value, which means I equals to half of this term, half of E over R. Okay, so for the RL circuit, we know that this is the time constant tau L. Tau L is L over R. L over R, which means that when T equals to this one, then which is like 1 minus E to minus 1, something like that, when E R I equals this one. When T equals tau L, so this one like this. This one is, if I remember correctly, it should be like 0.368. Yeah, it should be roughly about that because E is a 2.71828. So 1 over E would be something like this one, this value, which is somewhere around here. So this is called a time constant. Usually in engineering problem, we will say if T is larger than 5 tau, no matter tau L or tau C, then we will assume that this value is already the equilibrium point. This is a rule of thumb because you can imagine e to the negative 5 power will be really small. Yeah. So here, tau L is L over R, which is 53 milli over 0.37. So here it is 173.2 millisecond. Yeah. Okay. So we have this term 1 minus E to the T we are concerning, and then over tau L equals. We hope that it reached the half of this equilibrium value, so it should be equal to 0.5. We don't really need to care about the E over R because they will just cancel each other. So we only care about this term equals to 0.5 is okay. So if we move this term over and move this term over, so we have a E to the minus T over tau L equals to 1 minus 0.5, which is 0.5. And then we take log on both sides. So log and exponential will cancel each other. So negative T over tau L will be log 0.5, which is negative log 2. So negative will cancel each other. So finally, we will have T equals tau L times natural log of 2, which is 143.2 millisecond times natural log of 2, which is around 0.1 second. Okay. So next we talk about the energy stored in a magnetic field. In chapter 25, chapter 25, we learned the energy stored in the electric field. If you still remember that, if we have a capacitor, the energy UE will be half of CV squared. And here, we just change C to L and then change V to I. Then this is pretty much of it. And of course, if you want to see the rigorous proof, which is like this one, du equals P, dub is P. Yeah, so take the derivative with respect to the time for the energy will be the power, and then yeah, here it should be so P, the power is actually I times V, and then V for the inductor, V is L di dt. So we integrate this one. We will get this integration, and then and then we'll get half of Li squared, which is similar to the derivation for the UE. Okay, so here we have another sample problem. So it says a solenoid has an inductance with the same value if a 12-volt electromotive force is applied across the coil. How much energy is stored in the magnetic field after the current has built up its equilibrium value? Yeah. How much energy storage after the current has built up its equilibrium value? Okay. So for this one, I equals E over R, because for it is steady state, which means that it said the current has built up its equilibrium value, which means that T tends to infinity. It tends to infinity. So we only get this term here, which is actually 12 over 0.35, and which is 34.38. So this is the current, and using the UB equals half of Li squared, which is half of 53 millihenry times 34.3 quantity square. So this one is 31 joule. Okay, so this is easy. So the next one, after how many times constant will half of this equilibrium energy will be stored in the magnetic field? So this is different from the previous case. For the previous example, for the previous sample problem, it asks the half of its equilibrium value of the current. But here, the energy stored here is proportional to the square of the current. So the conditions are different. So here we will say UB half will be half of Li half square. So we would like to seek for this one, which is half of the total power here, half of the total power. So this is the total power. Okay, so we can simplify this one. We can actually cancel L on both sides, cancel this 1/2 on both sides. So finally, we will get I have to be I over square root of 2. This. Okay, so so we will have it to be I times 1 minus exponential 2 minus T is what we would like to find. And then T, maybe we can say it is T half over tau L. We would like to seek for this value. And yeah, and we can see that we can actually look at this one, and then we can cancel I on both sides. So here, we can just move this term over, move this term over, and then we will have a exponential to minus T half over tau L equals 1 minus 1 over square root of 2, which is a square root of 2 minus 1 all over square root of 2. So, so T half will be like, we can just take lateral log on both sides, lateral log here. So lateral log and E can cancel each other. And as much as we have this negative sign, so we take the reciprocal here. So we will have a tau L times lateral log of square root of 2 over square root of 2 minus 1. Okay, so we just plug in the value here. It is nothing but 1.23 times tau L, because it asks you how many time constant. So we actually need this value 1.2 times. So this is actually log square root of 2 over square root of 2 minus 1, which is actually 1.23 times. Okay. So next here we will see this. This one is about energy stored in a magnetic field. Energy stored in a magnetic field. So just we already mentioned that UB will be half of Li square. So here it also derive the equation like this one. Small UB is B square over 2 mu 0 mu naught. So if you still remember, for the capacitor case, it will be like U small UE, which is half of epsilon naught E square. So if you still remember the duality, I will say epsilon naught, you can change it to 1 over mu naught. And then E naught, E, you can change it to B, and then you will get this one. So actually the derivation here, we will use a long solenoid to derive this one as a special case, but generally it will be true. You might think that this UE and UB might be not really useful for solving the problem, but actually in chapter 33, when we talk about the electromagnetic wave, we'll talk about the Poynting vector, which is the power carried by the EM wave per unit volume. And we will make use of this two equation here. So actually, let's see how we can derive it for the long solenoid. So the cross section is A, and then the volume in this one is actually A times L. So which is like a cylinder. So we have cross section of A, and then the length is L. This is L. The cross section is A. The cross section area, I mean. The energy UB stored in the length L for the solenoid must lie entirely within this volume because magnetic field outside is approximately zero. So it still make use of this approximation. The B field generated by the solenoid is uniform inside the solenoid, but approximately zero outside. So moreover, the stored energy must be uniform distributed. Yeah. And so UB is the energy stored in the magnetic field per unit volume. Yeah. So for the small letter, it means the UB, which means the energy stored per unit volume of the field. Yeah. So which is actually UB over the volume, because we assume the energy is uniform over this volume. So UB is half of Li square. So we have UB to be half of Li square, and then we can rearrange it. Li square, we have Li square. 2AL, we have L times 2A. L times 2A, something like this. So we just rearrange the order, and then we try to separate in two terms. So here L is the inductance, small l is the length. And actually, L over small l is mu naught n square times A. Yeah, I think we have derived it before. Yeah, so we make use of this equation, so we can just plug in this one here. So we have this green one to be this one. So we just plug in that one here. And then we also make use of this one. This is the magnetic field generated by the solenoid. We talk about this in chapter 29. Okay, so actually this term, plug it here, so we get this one. So this is this term. And I, we can make use of this one. So we have I equals B over mu naught N, like this. So we plug this one here. So we have B over mu naught N, and then quantity square over 2A, which is this one. Okay, so we can make some cancellation. A and A can be cancelled. And then here we have N square. So N square and N square can be cancelled. Mu naught and mu naught square, we can partly cancel. So we only have 1 mu 0. And then we have also B square here. So altogether we have B square over 2 mu naught. So which is a duality with this UE, half of epsilon naught E square. So this is the energy density and energy density. Okay, so in the last part of this chapter, we will talk about the mutual inductance. Mutual inductance is somehow like a transformer. Transformer. Okay, so transformer, as I know, there are at least 3 meanings for the transformer. One you will learn in the electromagnetism or some power system, you use the transformer, or actually the transformer, another meaning is like the Optimus Prime. 变形金刚 Optimus Prime. And the third meaning, we have transformer in the AI area, the NLP, the natural language processing. So we use the transformer to do something like the language transformation, transform English to Chinese or whatsoever language you like to transform. So this is the third meaning of the transformer. But here we will use the transformer like the transform some of the power from a coil to another one. So here we talk about the mutual inductance. Before we have something like EL is negative. L di dt. So which is like the self-induction. This is the self-induction. Self-induction. Here the setting is different. So let's look at this left figure A first. So here we have figure A, which is like we have a battery here, we have a resistance, a tunable resistance, so that we can control the current here, and then this is an inductor. This is an inductor. So this is a RL circuit. We can actually move this tip along this tunable resistor so that we can change the current here. And in that case, if we change the current here, the magnetic field generated by this inductor will vary, and thus the magnetic flux going through this second coil will also change. And due to the Faraday's law, if this magnetic flux is changing over time, then there will be electromotive force generated through over this coil. So here we have a sensitive ammeter. Then we will be able to measure the current going through the second coil. So this is called a mutual inductance, which means that if we have some time varying current here, then there will be some power transferred to the second coil. And if these two coils doesn't change, and we put this ammeter to the first coil, and we put the battery and tunable resistance to the second coil, and we repeat the same procedure, then we will generate some current on the second coil, and this second coil will generate magnetic field, and then the magnetic flux for the first coil will also change. So we can also, using the same transformer, we can transfer some electrical power from the second coil to first coil. So the direction doesn't really matter. We can either transform from the first to the second, or from the second to the first one. So yeah, it's something to be like that. So if coil 1, coil 2 are near each other, the changing current in either coil can reduce an EMF in the other. So of course they should be close enough. They should be close enough, because you can see the magnetic field line. If it is farther away from this coil, then it will denser and denser, which means the magnetic field will be weaker and weaker. So these two coils should be close enough. And sometimes if you try to buy some transformer, then probably they will be just overlap together. Just maybe put this one inside the first coil, so that we hope most of the power can be transferred to the second coil rather than just leaking outside. So here, rather than this one, this is the self-induction. We have some modification to it. This is like M is called a mutual inductance. M is called a mutual inductance. This is the current of the first coil, the current of the first coil. and E2 is the electromotive force generated at the second coil. So this is the mutual inductance. Rather than this one, we have only a single coil here, and then this is the coil, the current of this coil, and then the EMF generated by itself. So this is called self-induction. And if it is mutual induction, we have a current at coil 1 generate an EMF at the second coil, and you can do it the other way around. We have current at the second coil, and then through the same mutual inductance, we generate EMF at the first coil. Okay, so here we have a sample problem here. So the figure shows two circular closed pack coil, the smaller radius R2 with N2 turns, being coaxial with the larger radius R1 with N1 turns in the same plane. So derive an expression for the mutual inductance M of this arrangement of these two coils, assuming that R1 is much larger than R2. So we can sufficiently assume that the magnetic field generated by the first coil is uniform. Okay, so here as much as we have a battery here, and actually this one is the first coil. This one is the first coil, which means that we have I1, and then we will have E2. We'll have E2, something like that. So we can keep this in mind. E2 equals negative M dI1 dt, something like this. Okay, so here we will try to find phi 2,1, which means that the magnetic flux generated by the coil 1 to the coil 2. So in this case, we should have D1, because the coil 1 will generate magnetic field. But we only consider the cross-section area for the coil 2, because we hope to find the EMF for the second coil. So we should use A2 here. B1 is the magnetic field generated by the coil 1, and then it is the effective area which will be absorbed by the second coil. Okay, so next, for the mutual inductance, we will have N2 phi 2,1 over I1. If you still remember, for the inductance, L will be N phi B over I. If you still remember in chapter 29, I think. No, chapter 30, this chapter. This is the definition of the inductor, which is the self-induction. Okay, so for the mutual induction, we will consider N to be the second coil, N2, and then phi B will be this one, phi 2,1, and then I should be I1 because it is generated by the first coil. So M has this expression, and we can just plug in phi 2,1 here. So we have N2 B1 A2 over I1, like this. And we will make use of equation 2926, which is like BZ is mu 0 I R square 2, and then R2 R square plus Z square to the 3 over 2 power. So I suppose we have derived this in chapter 29. We should also have derived this one, but in the E-field version for the electric dipole. So this one is for the magnetic dipole. If we have a magnetic dipole, if we have a magnetic dipole, this is I, this is I, this is A, and then along this Z axis there will be a magnetic field, which is like this one. This distance is Z. The radius of this loop is capital R, not square, yeah, like this. So this is the magnetic field generated by this magnetic dipole. If you don't remember, you can check back in chapter 29. Okay, so we make use of this one. Actually, these two loops are placed in the same plane, which means that we have Z to be 0. Z to be 0, which means that here B1 it would be equal to N1 times mu 0 I1 R1 square over two times Z to be 0. So this one will be R1 squared to the 3/2 power will be R1 cube. So this one and this one will be cancelled. So it will be N1 mu naught I1 over 2R1, like this. Okay, so we can plug in this one to here, because we have B1 here. Okay, so it will be like N1, N2, and then times I1 and I1 will be cancelled. We have A2 over 2R1. We still have a mu naught here. Yeah, like this. Yeah, we have this expression. Okay, so next, maybe we just we have this one, M equals mu naught N1 N2 A2 over 2R1, and then also for the second A2, it is a circle, so the area will be pi R2 square. And then also we plug in this one here, so it will be mu naught N1 N2 pi R2 square over 2R1. So we simply rearrange the term. We put pi mu naught in the front because they are constant, and then N1 N2, and then R2 square over 2R1 square. Okay, so this is the first case. we don't have enough space for the this one. Okay, so yeah, so this is up to the part A, and for part B, what is the value for M? We just need to plug in all the values here. So M will be pi, and then mu 0 is 4 pi times 10 to negative 7, and then times 102, 1,200, 1,200, yeah, square, and then times R1 is 15 centimeter, 2 times 0.15, and then R2 is 1.1 centimeter, which is 0.011. Yeah, and then square. So this is nothing but 2.29 millihenry. Okay, so this sample problem is a bit complicated. Okay, so let's move on. We still have two additional examples. Let's finish off this first before we have 10 minutes break. So it says a long coaxial cable consists of two thin wall concentric conducting cylinder with radii A and B. The inner cylinder carry a static current I, and the outer cylinder provides the return path for that current. The current set up a magnetic field between the two cylinders. Calculate the energy stored in the magnetic field of the end of the cable. Okay, so here we will make use of the this one, the line integral of b dot ds equals mu zero I. So if you still remember, this is the Ampere's law. We learned it in chapter 29. And then, yeah, similarly, we will use the simple case B times 2 pi r. Because we assume the magnetic field is at least the magnitude of the magnetic field is uniform over the whole path and parallel to the path. Okay, so mu zero I. So we have B equals mu zero I over 2 pi r. Yeah. Yeah. Yeah, actually, so this is the inner radius. This is the outer radius. So we care about the energy store between, yeah, here. Yeah. So is that the current set up a magnetic field between the two cylinders. So we have the current going from the inner radius for the inner cable, and then the other one will be the return path, which means that you can suppose the current in the inner cylinder is, for example, going outside. The I is going outside, and then the return path is going into the page. I is going outside, and then I is going into the page. One is going out, one is going into the page as the return path. So it is used for the relatively high frequency signal. We will need to use this coaxial cable. So co means 同轴, axial is 轴. So we have a inner cylinder and the outer cylinder. So for the forward path and the return path. Yeah. So if you draw the Ampere loop here, so we have we only include the inner current. So we just like this. Okay. So next one, we have UB to be B square over 2 mu naught, which is we plug in this one here. So we have a mu naught. One of it is cancelled with the one in the denominator. So we have a mu naught I square over 2. Altogether 8, because 2 square times this 2 is 8, and then pi square r square. Okay, so du is like dub is like ub times dV, which is UB is a mu naught I square over 8 pi square R square, and then dV will be R dr d theta dz. This is for the cylindrical coordinate. And so we would like to find the total energy stored here. So we just integrate dUB, which is actually mu naught is a constant. I square is also a constant, and then 8 pi square. And then we have a dr. We have r over r square. So we have 1 over r here. And then we need to integrate from small a to small b. And then d theta will be from 0 to 2 pi. And then dz will be from 0 to small l, because the length is l. The length is l. Okay, so finally, we will get this term. This one is lateral log of b over a. This one is 2 pi. This one is l. So finally, we have the answer to be mu naught I square, 2 pi and 8 pi square partly cancel. We have a 4 pi here. And then we have a lateral log of b over a. And then we still have L here. We still have L here. Okay, something like this. This is the expression of the energy stored in this structure. Yeah. Okay. So for the part B, it asks what is the stored energy per unit length of the cable if A, B, B. So we just need to plug in all the values. So we have a U. Actually, it asks you the energy per unit length. So we have UB, big UB over small l, which is mu naught I square over 4 pi, and then natural log of b over a, and then we plug in all the values. Mu naught is 4 pi times 10 to minus 7. So including this 4 pi in the denominator, we have a 10 to minus 7. And then I is 2.7, quantity square, lateral log of here 3.5 over 1.2. So finally, we will get 7.8 times 10 to minus 7 joule per meter. Yeah. So now we still have another one. Yeah, so here it says 2 parallel loops of wire have a common axis. Common axis means this is the center of the circle. This is another center of the circle. And if you connect them together, this is a perpendicular to this plane. Perpendicular to this plane, perpendicular to this plane. So we call it a parallel loop with the common axis. So common axis. The axis is like the line going through the center and then perpendicular to the plane. So smaller loop, the smaller loop with radius small r is above the larger loop with radius capital R by a distance x, which is much larger than this larger radius. So consequently, the magnetic field due to the counterclockwise current I. So we have a counterclockwise current here. In the larger loop is nearly uniform throughout the smaller loop. Because we assume this distance is quite long, then we can assume the magnetic field going through this smaller loop will be uniform. So suppose x is increasing. X is increasing means maybe the upper one is moving upward, or the lower one is moving downward, or the mix of them. Then x will be increasing. at a constant rate, V equals dxdt. Find an expression for the magnetic flux through the area of the smaller loop as a function of x. Here we also make use of this one. Just now we make use of this one, but we didn't have the assumption. We didn't have the assumption when z is much larger than r, because here we use z equals 0. But here, if we assume that z is much larger than r, then we can make some simplification like this one. So here, mu is the magnetic dipole of this one, which is I times the cross-section area. Okay, so here we can slightly rearrange this equation because the variable we use here are a little bit different. So we make some modification. Mu naught is still mu naught, and then 2 pi is still 2 pi, and then here mu should be I pi capital R square, because this is the source. We have a current here. Okay, and then z here is actually x, so we should use x cube rather than z cube. We have x here, and then it should be pointing to x-axis. This is x-axis, so we have I hat here. Okay, so phi b, we approximate it to be b times a, because actually the magnetic field at this point and at this point are not exactly the same. But here it assume that we assume that it is nearly uniform because x is large enough. So it is nothing but mu naught over 2 pi times I pi capital R square over x cube times a. A is actually this one, pi small r square. Okay, so we can do some simplification. Pi and pi can be cancelled, and no more. So we have 2x cube in the denominator, and the numerator we have mu naught pi I small r square and then capital R square, like this. So this is actually the expression for the magnetic flux. The expression for the magnetic flux, like this. Okay. So here we keep this in mind. Phi b is pi mu naught I small r square capital R square over 2x cube. Okay, here is asked, find B an expression for the induced EMF and the direction of the induced current. So we here need to make use of the Faraday's law. E equals negative d phi b dt. We only have a single loop here, so we don't have. We have n equals to 1. N equals to 1. Yeah. So we take the derivative of this expression with respect to time. So most of the term are constant. So we only have minus pi mu naught I R square capital R square over 2. This x is changing with respect to time. So we need to have d dt 1 over x cube, like this. Okay, so So actually, take the derivative is easy. So this is d dt x to the minus third power. So when we take the derivative, it becomes negative 3 times maybe negative 3 over x to the fourth power. And we have not done yet because it should be like the chain rule, because you can imagine this is something like f of x is x to the minus third power. So we have a df of x dt, which should be like df dx times dx dt, using the chain rule. So we have a dx dt here. Okay. So dx dt here is nothing but v. So we have a negative sign and negative sign, so they cancel each other. So we have a 3 pi mu naught I r square over times capital R square. And then here we have 2x to the fourth power, and then v. So this is the expression for the EMF. And here we need to determine the direction of the induced EMF. So actually here, for this loop, it is generate some magnetic field pointing upward. It should be something like this. And this one, you can assume it to be moving away from this loop, which means that at this point, we will assume the magnetic field is pointing upward and it is decreasing. Pointing upward and decreasing for this one, which means that the phi b is decreasing. And in this case, you use the Lenz's law, the EB induced by the smaller loop should be pointing upward, which means that you use the right hand rule. You use of pointing upward, then the current should be something like this. Which is counterclockwise. You just look at it from the bottom, from the top. Yeah. Or actually, you can also referring to this one. We don't ignore any sign, positive or negative sign here. And finally, we find that this one is a positive. And originally, the current is counterclockwise here. So here, counterclockwise is positive. So we have positive here. So this current should also be counterclockwise. And this is the end of this chapter. So let's have a 10 minutes break.